And okay, before I get into this, the final is Monday at 11 a.m. and I will put that on D2L today. Uh, it starts at 11, yeah. And I can be flexible for people who can't make that, especially people who are in D form also, because those are scheduled back to back. But I just always do my finals in 2 hour blocks instead of 3 hours. So count on it just being 2 hours long. Okay, so the one thing that is different about this problem is that, so I'm going to write down a coordinate system. I'm going to have the x-axis pointed this way and the y-axis pointed up, and then the z-axis is coming out towards us. And I'll talk about why I put it there in a second. But the one thing that's different here about the other problems is just if this coordinate system is rotating with this, with this piece as it goes around, just notice that the axis of rotation of the disk is not along any of these axes. Okay. And so we're going to have to use a unit vector to define the angular velocity of this disk. Okay. And we're just going to have to use the right-hand rule because the angular velocity is always in the direction of your thumb when your fingers do that rotation. In the direction, yeah, your thumb is going down and to the right. So the rotation is like this. And so if you know that the magnitude of that angular velocity is 40 radians per second, and you know the direction is this, you can just come up with a unit vector in this direction, multiply it by 40, and that's your angular velocity. Okay. Okay, so well, I wrote down the coordinate system before I talked about this, but there are two bodies here. One is the piece that rotates around the y-axis and has the downward diagonal piece. That's the horse in this problem. The cowboy is the disk. Because if you move the top piece to a different angle, it changes the axis of rotation of the disk. That's how you know. Okay. Vice versa, it doesn't work the opposite way. And so this thing is the horse, and this thing is the cowboy. And in order to choose where to put that coordinate system, really your last job is finding a point where the origin is not changing location. So there's no acceleration of the origin. And where I drew it, if you think of it that way, that the coordinate axes, if they're fixed to the horse, are just going to be rotating around a fixed point. And so that's a good place to put it. Any questions about that choice? Victor and Ken, you guys missed a lot of important information about the formation of early heavy metal music. It's not on the test, though. Okay, so now that we have this, we can say that the acceleration of p is equal to the observed acceleration of p plus capital Omega dot crossed with p plus 2 times omega crossed with the observed velocity of p plus capital Omega cross quantity capital omega cross P. And now we're just going to build our collection of things. We'll get the easy ones first and then get the harder ones. So what do we know about the angular acceleration of the coordinate system? We are told that, by the way, when I said 40, that was wrong. That's the thing for the disk, but the principle that I was talking about is still the same, but we'll get to that in a second. So we have this arm that rotates at 10 radians per second about a vertical axis, and it doesn't have any angular acceleration. And it says that the vertical axis is straight down. So that means that, so our thumb is pointing this way, the rotation is happening like this. And so this angular velocity vector is going to be in the negative y direction. So 0, negative 10, 0. Yes, that's why. Yep. Okay, so the first thing is there's no angular acceleration of the body. So this is equal to 0. The angular velocity is equal to 0, negative 10, 0. And the position vector, what's the definition of the position vector? Exactly. Yep. So from the origin to the point. And so we're going to have to do a little trigonometry here. I'm going to calculate the vector that goes from the origin to the axis of the disk. And then I'm going to add that to a vector that goes from the axis of the disk, the center of the disk, to that P. Okay, so I will write that as, so this is, the arm has a length of 0.6. So I'm going to go 0.6 times the cosine of negative 60 degrees, 0.6 times the sine of negative 60 degrees, 0. And then I'm going to add that to the radius of the disk is 0.2. And if you think of it as, so to think of the direction of this next vector, if this is your coordinate system, our first vector was like this. Our next one is perpendicular to that, so like this. And so if we're going to go negative 60, and then we're going to go counterclockwise, positive 90. So we end up with 0.2, was it, times cosine and sine of 30 degrees.
Can you explain that again? So why do you start it from -60?
Okay, so because what we know is happening here is we know that the vector going from the center of the disk to P is perpendicular to this. Okay, so I first came up with the vector that goes this direction. And then from there, I rotated counterclockwise 90 degrees to get to this vector.
Yeah.
So that's why it's -60 plus 90, and you end up with plus 30. Okay, so let me add these. And I got 0.473 negative 0.420. So that's our P vector. And now the things we have left are we have to calculate the observed velocity. And the observed velocity, we're ignoring the motion of the coordinate system now. And so all this coordinate system sees is P moving in a circular motion. So this is just going to be omega of the disk crossed with the R vector. And now we have to think about omega of the disk. Oh, 40 was the right thing to use there. Well, we know that the angular speed is 40 radians per second. Okay. And like I said before, we know that the direction of this angular velocity is straight down the arm of that thing. And so all we need is, so we have the magnitude, we need a unit vector for the direction, and then we'll just multiply them together. So I'll say, so omega is equal to 40 times, what's a unit vector pointing down that axis? It's just going to be cosine of negative 60 sine of negative 60. Anybody have any questions about that?
Yeah, why is omega isn't it just 40 on the
Yeah, like in along one axis or
Yeah.
something. Yeah, because the definition of an angular velocity vector is it's the angular speed times like a unit vector direction according to the right-hand rule. Okay, and so if we use the right-hand rule and we put our fingers curling in the direction of that disk, our thumb is pointing straight down that axis. And actually, I think in this problem, it even says the axis is straight down and to the right. You know, it's just going along that arm. But that's a helpful way to think about angular velocity, you know. And so now we have 40 times cosine of negative 60. And so this is 20, negative 34.641, and then 0. And now what about the R vector? Well, what's the definition of the R vector?
The center of the circular motion to where the work.
Yep, exactly. So this is just going to be 0.2 times the cosine of 30 degrees, 0.2 times the sine of 30 degrees, 0. And that is 0.17 173. 0.2 times cosine of 30. 0.173, yeah, 2 I'll put in there. And then this one is 0.1 and then 0. And now we can take this cross product and we get that the velocity of P that's observed is equal to 20, negative 34.641, bless you, 0, crossed with 0.1732, 0.10, cross those two. and you get 0, 0, 8. Okay, yep, that makes sense. And then the last thing we need is the acceleration of P that's observed in the coordinate system. It's circular motion, so this is the watermelon equation. This disk has no angular acceleration. So this part is equal to 0. And so our omega cross r, we already calculated as, well, our omega we got is 20 negative 34.641. And our omega cross r we've already calculated as 008. And so our observed acceleration is negative 277.13, negative 160, 0. And this is meters per second squared. This is meters per second. And if you look at what this is doing, we're just talking about a centripetal acceleration there. So it should have a big component in the negative x direction and a smaller component in the negative y direction. Come on. And that's what we got. I mean, we could do the inverse trig and make sure that that angle is right, but that looks plausible. So now we just have to put all this together. The acceleration of P is equal to the observed acceleration plus omega dot cross P, capital omega, but it's a constant angular velocity of the coordinate system, so this goes away, plus 2 times omega, so 20 negative 34.641, crossed with the observed velocity, which is 008. Plus omega cross the quantity. Let me put those in. So omega is 20 negative 34.641 crossed with the quantity 20 negative 34.641 crossed with the position vector, not the r vector, and the position vector is 0.473 negative 0.420. Capital omega, yes, I read the wrong one. So let's see, where do we have it? We have one here, and here, and here. So 0, negative 10, 0, 0, negative 10, 0, 0, negative 10, 0. And I got negative 484.43, negative 160, 0. Any questions about that? Yeah.
So since we had got negative numbers, does that mean slowing down or does it mean it's rotating?
This is an acceleration vector. So what that means is if you draw your coordinate system, that vector is, you know, in the negative x direction, 484, in the negative y direction, 160. So it's just an acceleration vector in that direction. Okay. And then if you want to make more sense of it, if you know what the velocity of the thing is, you know what the velocity of the point is. So say the velocity vector, so say this is the acceleration vector, and we didn't calculate the velocity of this thing, but let's just make something up. Let's just say that, okay, we calculated that the velocity vector is like this. Okay. Then you could break up the acceleration vector into a part that's parallel to the velocity and a part that's perpendicular. So you could say, so here is your parallel part, and here is your perpendicular part. And the parallel part of the acceleration, the part that's parallel to the velocity, tells you whether it's speeding up or slowing down. If it's in the same, if that component is in the same direction as the velocity, it's speeding up. If it's in the opposite, it's slowing down. And then this tells you which direction it's turning. This has to do with speed change, and this has to do with direction change. Any other questions? Okay. And then that's all. We just want the acceleration. Okay, I want to do an example that I think for a lot of people, this is something you've always kind of wondered about, you know. So we're going to use this rotating coordinate system stuff to figure out what's the error in accelerations measured on the surface of the Earth. And just to be clear, the error that I'm going to calculate is the error due to the fact that the Earth is spinning around its axis. There's a smaller error related to the Earth going around the sun in mostly a circle, close to a circle. Then there's an even smaller one due to the sun, and it goes on, but at least they get smaller as you go. So it would be a disaster if they got bigger as you went. But
the speeds like the sun spinning around in the galaxy and the galaxy spinning around in the universe, like aren't they like really,
And then the
really
universe
fast?
spinning around too.
Right.
Is that right?
Right. And then the universe is like an atom inside a giant, and the giant's walking. Yeah, exactly.
Yeah. It turns out the whole multiverse.
Yeah, right. But we're not worried about that. We're just worried about the Earth spinning on its axis. Sorry, Marco.
Yeah, aren't those like numbers get progressively bigger even though the distances also get larger too?
Yes, exactly. Yep. So you're dealing with very big velocities and stuff, but very big radii, so the accelerations aren't very big. Okay, what's the error in accelerations measured on the surface of the Earth due to the Earth's rotation about its axis? And so here's what we're kind of thinking about. So there's the Earth, and I'll think of that as the equator. And here's the center of the Earth. And we'll have an x-axis like that, a y-axis like that, and a z-axis like that. And the Earth is rotating this way if the top is north. And you know it's rotating this way because the sun rises in the east. And there are a few things that we know. We know that the radius of the Earth is about 6.0 times 10 to the 6.0 times 10 to the 6 meters. And we know that the angular velocity of the Earth, the way that I have it drawn, is, so the way you calculate the magnitude of the angular velocity is, you know that it does one rotation or 2 pi radians every 24 hours. So in radians per second, it's going to be very small. And you get, you can see the way I have it drawn, the axis of rotation is the positive y direction based on the right-hand rule. And so this is equal to 0, positive 7 times 10 to the minus 5, 0 in radians per second. And then for our point P, all I care about is, so like if this is the point P, okay, all I care about is the angle between these. So this is my angle theta. Okay, well, we know what the radius is because we're always on the surface of the Earth. We're not on the inside of the Earth, you know. And so P, I'm going to define as the radius of the Earth, 6 times 10 to the 6 times the cosine of the angle theta, and then 6 times 10 to the 6 times the sine of the angle theta, and then 0. And then I am going to say in our lab, which of course is fixed to the Earth, we measure and I'm going to say fixed to the center of the Earth, so that we're going to treat the origin of the coordinate system as a fixed point. We're going to say that we take some measurements and we're going to figure out what we have to add to those measurements to get a true acceleration. Okay. So our measurements are wrong because our coordinate system is non-inertial, it's rotating. Okay. So we get measurements I'll call it Vx, Vy, Vz. That is our observed velocity of the particle. And we also take some acceleration measurements, and I'll call those Ax, Ay, Az. And we want to know, you can think of it as like a correction factor. Not a factor, a correction term to add to the measured acceleration, the observed acceleration, to get the true acceleration. Okay, why do we want that true acceleration? We want it because we're going to use Newton's laws, Newton's second law. And if you have an acceleration measured in a non-inertial coordinate system, Newton's second law doesn't hold. Well, of course, it's just an issue of precision. In a lab on the surface of the Earth, you get pretty good values unless you need a super high level of precision. And you can, Newton's second law more or less looks like it works on the surface of the Earth, but it doesn't exactly. And so this is how much it's gonna differ from the true acceleration. Any questions about that?
Wait, when you say true acceleration and the other one is?
Observed acceleration.
That means we are out of the space, we are absorbed.
Yes, so that's saying somehow you have acquired a floating chair that has zero acceleration, and it just hovers there with zero acceleration, and so all the measurements your video camera takes are correct. And then those are the things you can use in Newton's second law. If you're taking your measurements on a chair that is accelerating, every chair in the history of the universe, that is, then your Newton's second law measurements are wrong. Okay, so here's what we have. So the acceleration, this is the true acceleration, is equal to the observed acceleration, and that's this Ax, Ay, Az, plus the time derivative of the angular velocity of the Earth, or the angular acceleration of the Earth, in other words. Well, what's the angular acceleration of the Earth? Think about this, it's still moving after 7 billion years. So I think it's pretty safe to call that zero, even though it actually is slowing down. We certainly can't detect it. So we have our omega dot crossed with the position vector, and this goes away. And then we have our Coriolis acceleration, 2 times the angular velocity crossed with the observed velocity, which is Vx, Vy, Vz, plus capital Omega cross quantity, capital Omega crossed with the position vector, which was r cosine of theta, r sine theta, and 0. And then we can fill in some of these values. But what we're trying to find is this stuff that we have to add to the observed acceleration to give us the true acceleration. So this is our correction term. And we expect this to be small. Okay, so the correction term. So we'll go 2 times 0, 7 times 10 to the minus 5, 0, crossed with the observed velocity, Vx, Vy, Vz, plus the angular velocity of the coordinate system. So 0, 7 times 10 to the minus 5, 0, crossed with the quantity 0, 7 times 10 to the minus 5, 0, crossed with 6 times 10 to the 6 times the cosine of theta, 6 times 10 to the 6 times the sine of theta, 0. And so we get 1.4 times 10 to the minus 4 Vz. 0 for y, and then negative 1.4 times 10 to the minus 4 Vx. And then we're going to add that to, so we have 0, 7 times 10 to the minus 5, 0, crossed with 0, 0, negative 420. And I still have that cosine in there. Cosine theta. I'm wrong.
Will this be on the test?
No, well, no, not really, but I mean, it's all part of understanding rotating coordinate systems, you know? Yes?
I did have a question about for the observed velocities and acceleration that we put in here. Now, if we are trying to find the true acceleration of something that is being affected by, where its axis
Yeah.
of rotation is being affected by some other movement,
Mhm.
then that observed velocity and acceleration would be that rotating coordinate system equation, right? Because that's what we observed.
Can you say that again?
Yeah, so
Okay.
if we were trying to measure the acceleration of some kind of points that, let's say its axis of rotation is being affected by some other
Okay.
rotating thing,
Yeah.
then what we observed
Okay.
is-
Yes. Okay. So what we are doing here is particle kinematics. And so I think you're sort of starting to get at thinking about rigid body kinematics, which would get more complicated than this. But I guess, I mean, if you think of it as like a horse and cowboy type situation, okay, yes, you could do that. I mean, you could apply this exact same approach to something that's in your coordinate system is also going through a different kind of circular motion or whatever. Yeah, you could definitely do that.
So it all like compounds on each other.
Yeah, you can do this all as a big compounding thing, and you kind of have to think of it as unraveling this system. So we've only done it with a horse and a cowboy, but you could have a tiny cowboy riding a bigger cowboy, riding a tiny horse, and then horses and horses. And what you have to do is just go to the first one out, the tiny cowboy, come up with that cowboy's acceleration, taking into account the rotation of the bigger cowboy. Now that's your observed acceleration in the next coordinate system. And so you start kind of at the middle of the onion and undo it. Yes, you can do that. It's 2 bodies is not the limit of this approach. It's just, but that's enough to understand or get used to doing for now, Any other questions? Okay, well, I'm not really going to give a homework assignment, but I think I will put on so there's nothing you have to turn in, but I think I will assign a video or 2 on mechanical vibrations. I promise you that not having seen mechanical vibrations is not going to be a big problem for you in your future classes, but if you're curious about it, I'll put a link to those videos and you can just sort of check it out. But we won't do any problems and it won't be on the test. Okay.
You consider that as extra credit?
Give us some problems.
No. Yes, I did just consider it, and the answer is no. So I will consider it. All right. Thanks for taking dynamics. Woo. Class is over. Yes, test is Monday at 11. And I will try to be available on email, and if you want to do any Zoom meetings or anything, I try to make myself available in the next couple days if you have questions and stuff. Okay.